G'day guys, and welcome back to Up to Speed with ElasticSearch. This is chapter 3 of the course. In the last chapter we looked at indexes. If you haven't watched that video and you'd like to learn a little bit about indexes before moving on to search, I'll put a link in the description. But this video is going to be all about search. And before looking specifically at search, I want to actually touch on something that might somewhat relate to indexes that we didn't cover in the last chapter, which is mapping. So in the last chapter, we copied a mapping from one index to another, but we didn't really go too deep into what makes up a mapping and what different fields are. And the reason for that is that they don't really make much sense unless you understand search, or unless you're about to talk about search. So when we talk about mappings in Elasticsearch, they kind of fall into two categories. You have non-analyzed fields and analyzed fields. So to start off with, we'll look at non-analyzed fields first because they're the simpler of the two. So I have a link in the slide that looks at a few different fields that Elasticsearch offers. And I have a few examples here of non-analyzed fields: Boolean, date, integer, keyword. There are others. But to bring up the page, here we have a few common types, and these are non-analyzed fields: binary, Boolean, keywords, numbers, dates, alias, and a few others as well. But I'd say the most common ones are probably Boolean, keyword, numbers, dates, at least in my experience. And I don't want to go over these too much because they function very similarly to how you'd expect coming from a relational database. If you perform a select star from a table where a Boolean field equals true or Boolean field equals false, that's going to behave the same way as a Boolean field in Elastic. Same thing with numbers. If you want to select a star from a table where a numeric field is greater than 5 or less than 100, that's going to work in the same way in Elasticsearch. Similarly for dates as well. The only one that I will talk about, because it's something that doesn't really exist to my knowledge in a relational database, is this keyword field. So keywords might make a little bit more sense when you contrast them to full text search fields or analyze fields, which we'll do in a second. But keywords, you could basically say, as the name might imply, for when you want to do a search and you generally are going to be doing an exact match. In other words, this is a specific keyword that you're going to be doing exact match searches for. So things like IDs, whether they're strings, numbers, or GUIDs, IDs generally you don't perform any kind of range queries on, or any kind of contains queries on, or certainly not any kind of full text search or analyze search queries on. You generally use IDs in searches when you're after an exact match. Find me all of the records that are under this particular account, or find me all the records that belong to this particular customer. You're doing an exact match search where the account ID or the customer ID is going to be a keyword. So I think that's enough to understand of keywords for now. Just keep in mind, whenever you're doing an exact match search, a keyword is generally going to be the field that you want to use. Even though we have things like numeric fields, if you have a number that you're going to be performing an exact match search on, I would consider indexing that number as a keyword. Keeping in mind that you can index one field in multiple ways. You can index one field as both a number and a keyword using subfields, which I'll demonstrate when we get to the practical part of the video at the end. So that's keywords, and that's non-analyzed fields. Nothing too crazy going on there. Analyzed fields are where things get rather interesting. So this is for a situation where you've got a whole bunch of text. Maybe this is a blog post, or maybe this is a comment, or maybe this is the contents of a book or contents of a web page or something like that. And you want to perform a Google-style search where even if what the user entered doesn't quite match potentially anything in the actual document itself, but it matches slightly, and you want to return results even if they don't match exactly, and you want to order them by their relevance, by how much they match. So page 1 of Google's search results, very relevant, pretty close matches. Page 10, not so relevant, not so great matches, but they are still returned in the results and they're ordered by that relevance. So how does this work? ElasticSearch has a process called analysis, which takes place only for analyzed fields. Makes sense? In other words, the full text search fields. And analysis has 3 stages to it, or 3 steps. The first step is to filter the characters that are in the text of the document that's being saved to the index, or filter the text that's being included in the search. So analysis happens at 2 stages. Once when the document is saved to the index, and once when you're actually performing an analyzed search. So the same 3 steps happen in both times, when the document is saved and when you perform the search. So first step is to run character filters. So character filters are going to filter the characters of the thing being saved or the thing that you're searching for. So it could do things like decode HTML, replace characters, similar things. So operating on the stream of characters that are coming through. Step 2 is to run a tokenizer. A tokenizer is going to take that filtered stream of characters and cut it up into tokens. And there are different built-in tokenizers that ElasticSearch offers, just like it offers some built-in character filters. Common ones that you might use are to break on word boundaries, or you could break on system paths, or you could break on some language-specific tokenizer to get more relevant searching for a specific language. And after the stream has been broken up into tokens, you can then run token filters. So token filters operate on, you can imagine, an array of tokens after the tokenizer has split up the character stream into like an array of tokens. The token filters can then filter those. So you can do things like remove white space tokens, or remove punctuation tokens, or lowercase all of the terms, add tokens that are synonyms of other tokens, and other interesting things. And those 3 steps work together to create intelligent searching. But I understand that you might not really be able to imagine what a sample piece of sample text might look like going through those 3 stages. So I have a small example for you. So we've got these 3 stages: character filters, tokenizer, and token filters. And I have 2 bits of example text. One is a string, the quick brown fox jumps over the lazy dog, and the other is a GUID. So I want you to just ignore the GUID for the moment, pretend that it's not there. We're going to focus on the text. The quick brown fox jumps over the lazy dog. So this is the raw text that gets saved into the index, or this is the raw text that you're searching for. And for argument's sake, we're not actually going to run any character filters on this stream of characters. The tokenizer is going to tokenize the string based off of white space or word boundaries. So the space in between the and quick is going to be used to basically break between those 2 words. So the is one particular token, quick is another, and so on for the remainder of the words, which are now tokens. And we then run an English style token filter, or a token filter for the English language on this stream of tokens. So the is considered a stop word in English. It doesn't really convey any value, so they're usually not included when analyzing full text search fields, because imagine if you jump into Google and you type in the, well, you're going to get all sorts of results. It doesn't really convey any meaning whatsoever. So we don't include them in the full text search at all, these sorts of words like the, it, they, etc. So that gets filtered out. Quick is still there, brown is still there, fox is still there, but notice how jumps got transformed into jump. So it got stemmed, and because we're optimizing this search process for the English language by stemming the token from jumps into jump, that means that we're able to return results from the word jumps, jump, jumped, jumping, jumper, all of those variations of the word jump. If you convert the variation into the word stem, which is jump, you're able to support searches for all of those different variations. So quite powerful and very tailored to the English language. I think the rest of the tokens haven't really been transformed all that much. So at the end of the day, we end up with these tokens: quick brown fox, jump over lazy dog. So if somebody searches for can quick brown foxes jump over lazy dogs, you can imagine they'll go through the same process. Dogs, for example, will get transformed into dog, and we'll be able to match on a sentence like the quick brown fox jumps over the lazy dog, even if somebody searches for can quick brown foxes jump over lazy dogs. Because of that stemming process, they'll get transformed into the same terms at the end of the day. So that works quite well for a sentence like this, but it works horribly for a GUID. If you take a GUID like in the second example, let's run through that same process again. So we don't have any character filters, just like in the first example. The tokenizer is going to tokenize on. It's going to break on punctuation, like these dashes, these hyphens, and you'll end up with an array that looks something like this. These hyphens are going to get removed from the end result, and you're going to end up with tokens that look something like this. So FE9 blah 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 is one token, CB52 is another token, 4D C6 is another token, and so on. And that is actually rather horrible, because if you try searching for a GUID that is actually not quite the same as this GUID, but maybe has the same phrase in it, the same token in it, you'll actually get matches if you try to do a full text search. Search on GUID fields, and you'll notice other strange behavior, getting results that you didn't expect, as well as not getting results that you did expect when it comes to doing full text search on GUIDs. So as we mentioned earlier, GUIDs are some kind of an ID. You're probably going to be doing an exact match search. So when it comes to GUIDs, store them as keywords, not full text search fields. Sharing a little bit of pain that I learned the hard way. So before going any further, I wanted to point out the type of field in Elastic that that supports full text search, basically. So coming back to this list from earlier, these are the non-analyzed fields that I introduced earlier. We do have some full text search fields as well, which are these text search types. So text in Elastic basically means analyzed full text search field. And the one that you use 99% of the time is just this simple text field. This is an analyzed full text search field. And you can configure different analyzers to work with this text field, which we'll see shortly. But if you want full text search, use a text field. If you don't, use one of the others. For an exact match, use a keyword. Okay, so we've gone over the process that happens behind the scenes when you're searching for a full text search field, or searching an analyzed field, or indexing an analyzed field. But how does Elastic actually find results? How does Elastic actually find, if you search for quick brown foxes, how does it find documents that match that particular phrase? And we've gone through part of the process, which is this analysis process. But the other part of the puzzle is this thing called an inverted index. So we're using the same example: quick brown fox jump over lazy dog. That's the output of the analyzer in the first example here: quick brown fox jump over lazy dog. What Elastic has behind the scenes is this thing called an inverted index, where it's an index of analyzed terms like quick brown fox jump over lazy dog, and an array of documents that contain those terms. So when document 1 was analyzed and stored in the index, if it contained the word quick in one of its fields, it would get stored in this inverted index. It would get stored in this inverted index for quick retrieval later. So after the analysis phase, once Elastic figures out, okay, these are the terms that we need to search for, it then consults the inverted index and says, okay, which documents contain all of these terms? And we can see we've got this lookup that Elastic will use to find which documents contain these terms. Now, an interesting exercise might be to ask, okay, what's going to be the order of the results? Assuming that we, as the person writing the query, don't modify the order, what's going to be the default order that Elastic returns the documents in? And I'm not going to go through each document, but I would like to highlight document number 7. Since document number 7 is appearing in the inverted index for each of these terms, that basically means that document number 7 contains each word that we're searching for. So the relevance of document 7 is actually quite high, and I'd expect document 7 to be the first entry in the results because it's the most relevant. Then you get others like document 99 appears twice, but let's say document 88. Document 88 only contains the word over. So it will be returned in results, but I might expect it to appear towards the end of the results and certainly not at the start. Document 7, I think, is the clear winner in terms of relevance because all of the words appear. So that's how Elastic then figures out which documents match your query. I do have a few links here for you. I'll put these in the description as well on character filters, tokenizers, and token filters. But I think that wraps up the theory for this session, and let's move on to the hands-on section. So I have a number of searching tasks for us to do, and searching is one of those things in ElasticSearch. It feels really weird when you first start doing it, but the more you do it, the more natural it feels. So we're going to run through these together. What I might recommend is after the video, try doing these again on your own without watching the video, and just get used to searching in ElasticSearch. It does feel weird at first, but you will get used to it. All right, so the first task that we have is to find all GET requests in the Apache index. So a thing that I like to do is whenever I have a task like this, I like to copy the task and paste it in Kibana as a comment, and then I don't lose track of what it is that I'm trying to do. So let's jump over into Kibana. We've got our console up and running, and here's our task: find all GET requests. And I might even prefix this with Apache index. So all of these tasks for the moment are for the Apache index. And if I check my indexes, we've got this Apache logs v1 index that we're going to look at. So when you're doing a search, I think it pays to do two things to begin with. Firstly, sometimes it's a good idea to just run an empty search, which is going to give you the first 10 results. And this gives you an idea as to what data is stored in the index. So our task here is to find all GET requests. And it looks like there is this verb field that we can use, which contains the HTTP verb. So that's probably going to be useful. The next thing that's worthwhile doing is looking at the mapping of the index, because as we've explained, if this is a full text search field, we're going to need to search things a little differently compared to if it's a non-analyzed field. So this HTTP verb, what is it? So I'm going to run a get Apache logs /_ mapping to retrieve the mapping. And we can see that the verb is a keyword, so it's optimized for performing exact match searches. Great, because that's exactly what we want to do. So find all get requests. We can do this now with get Apache _logs _search. We're going to provide a body to the search. So Elastic has a very specific domain-specific language when it comes to searching. We want to start with a query. This is basically going to contain all of the things that make up our search. And there are different types of searches that you can run depending on what you want to do. But because we want an exact match search, we're going to use a term search. And notice the Kibana is auto-populating a lot of the search for me, which is quite helpful, especially when you're starting out and you don't know the exact syntax. So the field that we're after is the verb field. And the value is going to be get. So let's run this. And we're getting back 9,951 results. This is a get, this is a get, this is a get, this is a get. That seems to be working pretty well. Okay, so I'm going to say that task is done. Let's move on to the next one. Find all requests which had a successful status code, so 2XX. Let me just drop this comment. Find all requests which had a successful status code. So I'm going to do the search again. We've got this response field, which seems to contain the status code, so that looks like it could be useful. Let's check the mapping of the response. It's a long data type, so it's optimized for numeric range searches. You can perform exact match searches on this, but if you wanted something to be optimized for exact match searches, keyword is probably the better choice. But it's a long numeric data type, so we can perform range searches on this. So let's go ahead and do this again. Get Apache logs _search. We're going to provide a body. We're going to provide a query, which is going to contain our search. And the type of query that we want to run here is a range query. We want to get everything between, say, 200 and 299, because we want all of the different variations inside that HTTP success status code range, which is from 200 to 299. So we'll run a range query. The field is going to be the response. We want it to be greater than or equal to 200 and less than or equal to 299. Let's run this. Cool. We're getting back 200s, 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 200s. A lot of 200s, but that does make sense since it's a pretty common status code. We're getting back 9170 results. Just for fun, let's modify this to 201 just to make sure that the range is actually working and we're getting back results other than 200. So if I run this, we get back 206 a few times. So I think I'm pretty happy with the results. They're coming back. There are only 45 results, so the vast majority of those 1,900 or whatever were 200 responses, which makes sense and sounds good. Okay, so that's a range. What's the next task? Now we are getting interesting. So we want to find all post requests which had a successful status code. So there are actually two parts to this query. We want to find all post requests, and those post requests must have had a successful status code. So this is like a compound query. So I'm going to copy this and I'm going to paste it. Find all post requests which had a successful status code. So we'll do the same thing again. Get Apache logs _search. We're going to specify a query, and in order to perform a complex query where you've got multiple conditions or optional conditions, or maybe you want to perform a query where something is not true, you want to use a bool query. So bool allows you to do all of those things, and it has three parts to it. It has must not, and should. And we're going to explore each of these throughout the next couple of tasks, but the one that we want at the moment is must. So all of the data that we want to retrieve must have a post verb, and it must have a successful status code. So the first part of the query is we're going to do a term query. The field that we want to operate on is the verb, and the value should be, or the value must be, post. So let me run this, and we get back 5 results, not many posts. One of them is a 200, another is a 404, another is a 404, another is a 404, and another is a 200. So these 404s should be stripped out after I add the next part of this query. So the next part, which is just another entry, another object entry in the must array, is going to be this range. Same thing as the previous example. I am going to type it again just so that you guys can see it. So range, the field that we're going to operate on is the response. We want it to be greater than or equal to 200 and less than or equal to 300 or 299. There we go. Let's run this. And now we get back 2 results. It's a 200 and it's a 200. So those 404s got filtered out. Awesome. That seems to be working well. I understand that I am going a little fast, but try to follow along, and don't feel bad if you do need to rewatch this video or practice these again yourself. I certainly didn't remember all of these after watching one video. It takes practice. So the next task, find all requests with a successful status code which were not GET requests. All right. Let's drop this down here, and we're going to start this the same way again. Okay, so we've got a similar sort of situation to the last time, where it's going to be a compound query. So that means that we're going to be using our friend the bool query. And maybe let's start with this. Maybe we can start with successful status code first. So it must have a successful status code. So we're going to use a must, and this is going to be a range. The field is going to be response, greater than or equal to 200, less than or equal to 300. Let's run this. And we're getting back 9,170 results. And I imagine that most of these will be GET requests. So we can see the first 3, the first 4 are all GET requests. So we want to filter these further to those that are not GET requests. Now, how can you do that? Well, maybe you could have another entry under must, which says that maybe the verb must fall within, you know, a range of post, patch, head, and so on. But that's a little messy, since it's very easy to leave an option out of that list. What we'd rather do is to do exactly what the question says. Find those which were not GET requests, which you might have imagined is going to be a where are we? Here it is. Must not. And must not basically will run just regular queries like what we've run before, but if any of them return results, those results will be filtered out. So must not, we can use a term level query, and the field that we're looking for is the verb. and the value is get. So if any whatever results got returned that match this query are going to be filtered out of the response. So let's run this, and we get back 35. That makes sense. And we have head, 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 head. Yeah, okay, mostly heads. I think that's working well, and yeah, that's we're basically now combining must and must not in our query. So you can see how this bool query is quite powerful. I think we had one or two left. One left on the Apache index. We want to find all requests which contain either 404 or a 500 status code. Okay. There we go. So we're going to start this the same way. Get Apache logs underscore search query, and we already know this is going to be a bool. Now things are a bit different this time because we've got this either situation. So either this query must match or this query must match. So it's kind of like an either situation. So must and must not don't really fall under that situation. If you had two entries under must, both of them must be true. Whereas what we want now is either of them must be true. So we can use should. And before we forget, I want to add an extra section at the end, which is minimum should match, and we're going to set this to 1. So what this is saying is we're going to have 2 queries in our should array, and at least one of them should match for that result to be considered valid. So the first one is going to be a term level query, and we're going to run this on the response, and the response should be 404. You know what, let's actually take this out and just run it right now. So we're getting back 213 results, and we're getting back only 404s. So let's go ahead and modify this now to also include another term query, an exact match query, where the response is 500. Let's run this, and we're getting back 404, 404, 404, 404, 404, 404, 404, 404. Are you going to give me any 500s? No. But if I take this out, we are getting 500s. They're just at the end. They're just at the end of the list. Okay, so that's how you do. You could say an or, search for one thing or another thing, and that wraps up our tasks on the Apache index. Now we're going to look at some tasks in the Shakespeare index, and you might have noticed all of the searching that we did in the Apache index was non-analyzed searching. So it was all exact match searching. In the Shakespeare index, where we've got more text to play with, we're going to do more full text analyzed searching. So I'm just going to copy the first task that we have. Shakespeare index. And the first task is find all documents that mention Prince Henry. I'm going to do the same thing again. I'm just going to start with doing a search. So something that mentions Prince Henry is probably going to be in the text entry field. So this is the play name. It's always going to be Henry IV. We're probably going to be looking at the text entry field. And let's just have a look at how that's mapped. So if I do a get Shakespeare underscore mapping and I run it, we can look for text entry, and it's of type text. In other words, it's an analyze field. It's a full text search field. I'm just going to have a sip of coffee. Awesome. So that means that this is going to play nicely with our full text search searching. Find all documents that mention Prince Henry. So let's create a new request. Get Shakespeare underscore search. We're going to run a query. This time we want to do a full text search query. So when we were using term earlier, that was for an exact match, non-analyzed query. Now we want to do a full text search analyzed query. So we're going to use a match query instead. And the field that we want to look at is the text entry, and we want it to match on Prince Henry. Let's run this. And we get exit Prince Henry, enter Prince Henry, exit Prince Henry, enter King Henry, Prince Henry, and others. This is an interesting one. Yeah, I think that all looks fine. Yep. Okay. I think that all looks fine. We can move on to the next task. So our next task is we want to find all documents that mention enter Poins. Poins is one of the characters in the play. So I think I can just copy this and change this from Prince Henry to enter Poins and run it. And we get enter Poins, re-enter Poins. This is interesting. Notice how even though we've searched for enter, it's also finding re-enter, and that has something to do with the analysis process that we talked about earlier. So re is going to be a token, enter is going to be another token, and points is going to be another token. So the fact that re is also in the document doesn't really matter. Now, it is less relevant than enter points. This is it matches 100% what we searched for. So this is more relevant than this, which mostly matches but has this extra token in it here. And you can actually see this happening. Notice how each record has an underscore score field. So this is ElasticSearch's calculation of the relevance of the record. So this has a 12.37, this has a 13.32, because the terms or the tokens that are in the document are an exact match of the terms that are in the search. This is almost an exact match, but it has one extra token at the start. Okay, let's just review the results. Here we've got enter Prince Henry and Poins. So we can see this has slightly less relevance. And it's got this stuff in the middle. It's got Prince Henry and. So we searched for enter Poins. So enter as a token on its own matched what we searched for, and Poins as a token on its own matched what we searched for. And the document just has these two extra tokens. So it's still matched, but it's lower in the results. Sometimes though, you only want documents that match an exact phrase, and you don't want this this sort of behavior. And so you only want documents that contain exactly enter Poins, and you don't want, for example, enter Prince Henry and Poins to appear in the results. So you can achieve this by using a slightly different search query. So you can use match underscore phrase instead of match. And if we run this again, we get enter Poins, re-enter Poins. So re is considered another token, but enter and Poins are an exact match of this phrase. So there can still be content before the phrase. There can still be content after the phrase, but the phrase itself must match. If you want literally an exact match of enter Poins, then you can use a term level filter. Although I think this may return no results because of the case, because of the casing, but you can run a text entry. Hold on a second. This is going to be term level query. Hold on, let me run this again. Term, the field is going to be a text entry. The value is going to be enter points, and we can case insensitive true. Should be able to do something like this. Maybe not. Possibly, I think this got added in a later version of ElasticSearch, if I'm not mistaken. Let me just search this. Do a term level query. Term query. Here we go. For version 7.10. Yeah, case insensitive is there. I guess enter points actually is never mentioned in that exact phrase. Let me undo this a couple times and see what we had. Yeah, okay, I'm happy with that. Yeah, that is kind of interesting. It could be that our Elastic version is too old to exactly match that. We can even, yeah, I think I'm not going to spend any more time looking into that. But if you want, generally, if you want to get literally an exact match, yeah, if you want literally an exact match, use a term level query. If you want, more flexible searching, use a match style query. I'm not entirely sure right now why we weren't able to search for enter points with lowercase values, but maybe we can come back to this. I might leave a comment on the video afterwards if I find the answer. So that's that. Let's sort the results by line ID in ascending order. I'm just going to drop this here because we can reuse the same query. So right now, the results are sorted. You know what? Let's run this on Prince Henry. So right now, the results are sorted by the score, and we're getting line ID 2224, 2768, 2941, 3092, 1831. So it's not in order of line ID. So let's go ahead and change that. We can specify a sort at the end, where the field is going to be line ID, and the order is going to be ascending. There we go. So now we're sorting by line ID in ascending order, which you'll probably need to do from time to time. And you can see this sort array has been added, which contains the sort field, or the sort value. So that's looking good. We would like to return the top 50 results. We can specify a size, and we want to set this to 50. By default, we're actually getting like 96 results, but by default, Elastic will only give you the top 10, but you can increase this up to 10,000. 10,000 is the maximum number of results that you can ask for. So let's go ahead and run this, and we're getting back now 50 results. And let's also exclude the speaker field. So right now we're getting this speaker field in the results. Let's exclude that. So we can do this by saying source excludes, this can be an array if I'm not mistaken, speaker. And if I rerun this, you can see that the speaker field has disappeared. I was intending to actually demonstrate using a custom analyzer in this chapter as well, but I think we've probably covered enough for one chapter, and I might leave custom analyzers to the next chapter. So I strongly encourage you guys to try completing all of these tasks yourselves as well. We haven't made any changes to the index, so they should all still run just as they ran here. And I'll see you in the next chapter where we will continue looking at search. Thanks a lot. Bye.